Inferential statistics regards using the sample data to make predictions about the population. The idea is that we're going to take what we did in the first day of class where we were gathering data, organizing it, and now instead of just showing you what's already there, we're going to use what's there to make predictions about the larger population. So one of the ways we're going to do that is with linear modeling. Linear regression for two variables is based on a linear equation with one independent variable. The equation has the form y equals a plus bx, where a and b are constant numbers. The variable x is the independent variable. It's the one we get to choose. And y is the dependent variable. It's the one that results from what we've chosen for x. Typically, we choose a value to substitute for the independent variable and then solve for the dependent variable. For each of the following situations, try and figure out which is the independent variable and which is the dependent variable. Remember again that the dependent variable depends on the independent variable, so we put something in, and based on that independent variable that we chose, the dependent variable has a result. In A, a study is done to determine if the average speed of a driver changes based on the driver's age. In B, cell phone bills vary according to data used. And in C, television companies base their prices for their televisions off the size of the television. Take a minute, see if you can think about which is the dependent, which is the independent variable for each. For part A, here they're using the driver's age in order to determine the average speed. That means the variable we get to choose is we're going to input the driver's age. And then we're going to see if the average speed changes both based on that age input. So that makes our choice the independent variable, driver's age, and the result, the dependent variable, speed of driver or average speed of driver. For part B, cell phone bills vary according to data used. We're going to input how much data we used for the month. The cell phone bill is going to come back as our output. So basically, as the two variables, our independent variable would be data used. Our dependent variable would be cost of cell phone bill. For part C, television companies base their prices for their televisions off of the size of the television. We get to choose how big we want the TV to be. They tell us how much it's going to cost. So the independent variable that we're choosing is the size of the television. The resulting dependent variable is the price of the television. Slope and y-intercept of a linear equation are important to understand in context. So for a linear equation, y equals a plus bx, b is the slope and y is the intercept. What b represents, the slope or the steepness of the line, is it represents the change in the y variable as a result of a 1 unit change in the x variable. If we used one of the examples from the previous page, for each additional gigabyte of data you use in your cell phone plan, you get charged another $7 a month. So in this case, the change in the y variable, $7 a month, results from the change in the x variable, 1 additional gigabyte of data use. The y-intercept is the starting point of the line where it crosses the y-axis. Or in the context of the problem, it represents the y value that results from an x value of 0. Using that same example, if we were going to talk about a cell phone bill, we would say that before you've used any gigabytes of data, there's some activation fee or set amount that you're paying per month that's a flat fee. So maybe you pay $10 a month plus $7 a gigabyte. Those numbers might be ridiculous. It might be $7 a terabyte. I honestly haven't looked at my bill in a while, but basically the intercept is what it would cost if you use 0 for your X. So in this case, the cost of the cell phone plan before you've used any data. Due to erosion, a river shoreline is losing several thousand pounds of soil each year. A linear equation that expresses the total amount of soil left after x years is y equals 180,000 minus 12,000x. What are the independent and dependent variables? How many pounds of soil does the shoreline lose in 1 year? And what's the y-intercept? Interpret its meaning. Again, I'm going to give you about 20 seconds here to think, try and plan out what your answer would be, and write it on your Cornell notes. The independent and dependent variables, here the number of years that have passed determines how much soil is left on the beach. So, or on the river, I should say, river shoreline. So here I would say that the independent variable, the one that we get to choose, is number of years or just years. And the dependent variable, the result of that is pounds of soil left on the shore. For how many pounds of soil does the shoreline lose in a year? This is really just another way of asking me the slope. 1 year is a 1 unit change in the x variable. In front of the x in the equation is a negative 12,000. So that tells me that the shoreline loses 12,000 pounds per year. Part C, what's the y-intercept, and interpret its meaning? The y-intercept is what we would get if we put in 0 for x. If we put in 0 for x, the 180,000 would still be on the right side of the equation. What that's telling us is here when we begin, after 0 years of erosion, there's 180,000 pounds of soil, or yeah, 180,000 pounds of soil on the river shoreline. So in this case, what's the y-intercept? 180,000. It means the amount of soil there before the erosion begins. Normal distribution is the most important distribution in statistics. It's the most heavily studied one, and it's the one that explains a lot of things that go on in the natural world. So we spend a lot of time on it in my statistics class. I'm going to give you a very quick introduction to it here, but I assure you it's incredibly useful and important. Normal distribution is bell-shaped and symmetric about its mean. It's completely defined by its mean mu and its standard deviation sigma. The total area under a normal distribution curve equals to 1. That's really saying 1 is a decimal. That just means it contains 100% of the things that could happen. Because if we change 1 as a decimal, 1.00, to a percentage, it would be 100%. The x-axis is a horizontal asymptote for a normal distribution curve. What that basically means is that you can never go below the x-axis because essentially that represents the zero line for probability. But to be an asymptote, it means it goes on forever in both directions, getting closer and closer to that axis without ever touching. Basically, this is a way of saying that we can get really, really big or really, really small answers that are way far from where we expect, but they occur with such small probability that they're incredibly unlikely. It would be like if we looked at the normal distribution for average amount that an American makes in a year, and then we wanted to put where Jeff Bezos would fall on that. We'd have to go 7 chalkboards over to find where he falls on the distribution because of how much money. So this is what a normal distribution looks like. What the percentages there below represent is how much of the data is contained within that number of standard deviations. So basically, when it says 68% of the data lies within 1 standard deviation of the mean, that's 1 standard deviation to the left, 1 standard deviation to the right. So this area around the mean is equal to 68% of everything that can happen. If we go 2 standard deviations out from here to here is 95% of everything that can happen. And if we go 3 standard deviations out, 1, 2, 3, 1, 2, 3, then between these is 99.7% of what can happen. Standard deviation really in its most basic terms means on average how far is something away from the mean in the data set. So if you're 1 standard deviation in either direction, you're pretty close to what you expect it to be. If you're 2 standard deviations slightly further, 3 begins to be something that you're very unlikely to see. But again, you could see something much, much further away from that. So if we were doing the average salary of an American, and let's say it's centered at $50,000 is the average salary, if we randomly select somebody, it's possible that we're up here and find somebody who's making $1 million a year. Much less likely that we find somebody making billions of dollars a year. So essentially, this is showing me that the most likely person we're going to find is somebody making 50,000. We're less likely to find somebody making zero or negative money that would be down here. We're more likely to find somebody close to 50,000, like somebody making from, let's say, 40,000 to 60,000, depending upon how the distribution lays out. So what the normal distribution shows us is from a certain x value to the left, what's the probability that somebody falls in this region? So if I know that this is centered at, let's say, the average height of a college student, and the average height is 5'9", which I'm going to call 69 inches, then if this is the average height of 69 inches, maybe this X represents 65 inches. And this shaded area would be everybody who's less than 5'5". And we would expect that only 27% of students on a college campus are less than 5'5" tall. That's the kind of thinking that we do with a normal curve. That's the kind of math that we're able to do when we really delve into what's behind the normal curve. We're able to take numbers that tell us here's the mean and standard deviation of a distribution and convert them to say, given that mean and standard deviation, what's the probability that I randomly find somebody from the population that's less than this amount? Additionally, we use tables like this, and in my class, I absolutely make students use tables like this to look up every possible z-score and figure out if I'm this much above or below the mean, here's what the probability of that occurring is. But I would say that it's more likely you'd use a computer program or a calculator to do this stuff nowadays. After making the full table, there's some common critical values that are found. Basically, if you want to be 80% confident that it's within that range, it would be a z critical value of 1.28, which means that if you're 1.28 standard deviations to the right, 1.28 standard deviations to the left, between those is 80% of everything that can happen. The way that you use these critical values is as we go to make confidence intervals and hypothesis tests that we're going to get into, we basically use the formula and we use the chart underlying it to say, hey, we tried to test and say, is it true that on average 1% of people die from contracting the coronavirus? And we found that no, in reality, only 0.01% die. If we were able to show that claim, 0.01% would be so far away from 1% that we could statistically say, no, it's not true that only, or that as many as 1% die from the coronavirus. So it's a convoluted example, but basically what I'm trying to say is these critical values will come into play by telling us how sure are we of a conclusion? How confident statistically are we that what we're trying to prove has been proven? So the way that we create a confidence interval is we start at the mean, we move a certain distance either way from the mean, and then we use the normal distribution to say we're this percent confident that this controls the true percentage within the population. So a confidence interval is always stated between a lower bound number and upper bound number. So maybe we could say we're 95% sure the average height of a college student is between 67 inches and 71 inches. That's the type of statement that we're trying to make. You've definitely seen them in your life if you followed any type of politics whatsoever. Anytime they tell you what percent of the vote somebody's going to get, Biden has 51% of the vote, Trump has 47% of the vote, with a margin of error plus or minus 3%. What they've told you is a confidence interval. That margin of error plus or minus 3% is what gets you to the lower bound or upper bound. And all of it is wrapped up in using this normal distribution in order to make these statements and make them statistically correct. So if you want to be 90% sure of something, that means you'd have 5% of the time you were wrong on either tail. If you want to be 95% sure, you'd have 2.5% of the time you'd be wrong on either tail. When I say that you'd be wrong, Basically, if I'm 90% sure that the true population mean is between 5'7" and 5'11", it's possible that I got a really short sample or a really tall sample. And for that reason, I didn't actually capture the true population. I went to the basketball team locker room and recorded all the heights there, and I found 20 students who were all between 6'1" and 6'3". My graph might show me, oh, the average height of a college student is much taller than I expected. But in reality, I'd be occupying one of these tails where by random chance, I ended up getting a sample that was far away than what it should have been. What the confidence interval process tells us is, based on the sample that we took, we're 95% or 90% sure that the true population mean lies within this range. So when we have a margin of error of plus or minus 3%, Biden is somewhere from 48% to 54% of the popular vote, based on the survey that we did where we found that he would get 51% with plus or minus 3% margin of error. When you interpret confidence intervals, the way that you say it is, we are this percent sure, confident that the true population value lies between the lower bound and the upper bound. What it really means is if we took repeated samples at the same size and used the same methods to create the resulting confidence interval, the confidence percentage represents what percentage of our intervals created would contain the true population value we were looking to isolate. So, interpret the following confidence intervals. 90% confidence interval for the price of a statistics textbook, 77.50 to 122.50. 95% confidence interval for the proportion of Democratic voters who will vote for Joe Biden in the 2020 Democratic primary, 0.3248, 0.3648. So what I'm going to do is I'm going to do the first one for you word for word, as you should write it in your notes, and then have you guys get a chance to try and do the second one. We are 90% sure that the true mean price of a statistics textbook is between $77.50 and $122.50. I'm going to repeat that. We're 90% confident that the true average price of a statistics textbook is between $77.50 and $122.50. I want you to try and write a similar statement for number 2. So the way I could write number 2, and it's absolutely fine if a couple words are different, but you have the same general idea. We're 95% confident that the true proportion of Democratic voters who will vote for Joe Biden in the 2020 Democratic primary is between 32.48% and 36.48%. You absolutely could write it just as the proportion, say, is between 0.3248 and 0.3648. I put it into percentages because that's the way you'd be more likely to hear it on a news broadcast, but either is mathematically correct. The idea of hypothesis testing, which I teased a little beforehand, is we make a hypothesis that we want to disprove. So this gentleman's a teacher. He comes into a statistics class day 1. He looks around the room at his students and he says, I believe the mean age in this room is 50. So in order to prove his hypothesis, he takes a sample, finds out, wait, the actual average age of the room is 20. If the average age was 50, you'd be very unlikely to find a sample with an average age of 20 if you're using proper sampling methods. Therefore, you reject the null hypothesis. Now, in my drawing here, the man looks angry. He shouldn't be. Really, rejecting a null hypothesis is the goal of a statistician. It's a little different than how your thinking would normally be with hypotheses. If you're in a science class and you want to prove that this element burns at a Bunsen burner temperature of 200 degrees Fahrenheit, then you go about putting it at 200 degrees Fahrenheit and hope what you said happens. In statistics, it works a little differently. In statistics, we start with the null hypothesis that we want to disprove. If we disprove it, only then can we say the alternative must be true. So the goal is pick something that you think isn't true to disprove and use that as a way of proving the alternative. Again, it's a little tricky at first to understand how the thinking goes, but it's important to look at studies in the future that may have an impact on your profession, may have an impact on other parts of your life, and understand what does that p-value really mean? How do I know how sure they are of the results of this study? So we start by creating a null hypothesis. The null hypothesis, denoted H0, represents the hypothesis that will be accepted unless the data provide convincing evidence that it's false. This usually represents the status quo or some claim about the population parameter that the researcher wants to test. If it turns out that we can't statistically disprove something, that doesn't mean that the null hypothesis is true. Statistical process can only disprove things and support an alternative hypothesis. If we're unable to disprove the null hypothesis, here it says that it's going to be accepted, but it's not really accepted. It's just kind of set aside and said, all right, we weren't able to disprove that. Statistically, we can only prove stuff by disproving. So when you state the null hypothesis, you set it up as H0 colon, and then whatever the population value, in this case, it's a population mean. That's why it's got that Greek U, or I'll pronounce it mu, equals some value. So maybe the null hypothesis would be mu equals 50, the average age in the room. Where the value we are setting is equal to is actually something we want to disprove. So we want to disprove the average age is 50 because we know it's actually smaller. We set up as the null, mu equals 50. The alternative hypothesis, denoted HA, represents the hypothesis that will only be accepted if the data provide convincing evidence of its truth. And this is what we want to prove. It represents the values of a population parameter for which the researcher wants to gather evidence to support. So our goal with an alternative hypothesis is to say the average age in the room is less than 50. Maybe we want to get the sample that shows it's 20. That's so far away from 50, we've been able to prove and can statistically publish with some probability next to it. We're 99.999% sure that the average age of a college student is less than 50 years old. The opposite of the null hypothesis is the hypothesis that will be accepted only if the data provide convincing evidence. Designate HA, and I can go one of the following ways. I can either say the mean is not equal to the hypothesized value, where I'm not sure if it's less, I'm not sure if it's more, I'm just saying not equal to for now. Or I can specifically say I think the mean's less than the hypothesis value, or I can specifically say it's more than the hypothesized value. I think you can see reasons that you'd want to test something as being less than or more than. As far as the not equal to, my favorite example for that is maybe you run a factory that's producing cereal boxes, and you want to test whether or not the 16.3 ounces you list on your container is how many ounces are put into your actual cereal box. You randomly select 100 boxes off the factory line and you weigh them very accurately on a scale to see how many ounces of cereal you're giving your customers. There, you'd be concerned with each of the two things. If you're doing these weights and you find out that you're giving customers 15 ounces and telling them it's 16.3, that's false advertising, that's a problem. You need to change, you need to put more cereal in the boxes. If it turns out that you're giving the customers 18 ounces and you're only advertising 16.3, well, there's two possibilities. Either you want to cut back how many ounces are in the bags to make sure you're not wasting product, or you want to advertise that there's 18 in them. Because if you're giving away more than is on the box, you want people to know that you actually have more that you're giving. So in that situation going in, factory owner doesn't know which way it's going to go, but is interested in both. There's many different situations where a two-tailed test or a not equal to test makes sense because you're concerned with either it being too high or too low. Set up a null and alternative hypothesis for each of the following situations. So I'm going to do the first one for you, then give you time to try each of the next ones. Mean age in this classroom is less than 20. Where I'd want to begin is by stating the null hypothesis, which is H0 colon mu equals 20. It's always the case that your null is equal to. never is your null going to be anything other than equal to. You do have to make a choice between a mean and a proportion. A mean, you're going to use what looks like a U or a Greek U with an extra tail. A proportion, you're going to use the letter P. So in this case, it's a mean. That's how I know I'm going to use mu for the mean. I'm going to set it equal to 20 because that's the number I'm being compared to. I then underneath that would write HA colon. Here I'm trying to prove that it's less than 20, so my HA would be mu, a less than sign 20. HO, mu equals 20. HA, mu is less than 20. I'm going to do the second one as well, just to talk you through a proportion. More than half of this class went to high school in Montgomery County. So we want to start out by stating it as an equal to. So I would write it as H0 colon P equals 0.5. 0.5 representing half as a proportion. So HO P equals 0.5. HA P is greater than 0.5. If it's more than half I'm trying to prove my alternative, I'd use a greater than sign to show that. I want you guys to try the third, fourth, and fifth bullets. Average number of students per class at Monco is 25. 32% of adults believe that 16-year-olds should be tried as adults, and less than 3/4 of the day is spent awake. The first one for the average number of students should be a mean, the 32% should be a proportion, and the less than 3/4 should be a proportion. Work on those, and then I'll say the answer. For the average number of students per class at Monco is 25. You would want to do H0 colon mu equals 25. Since it doesn't tell us we're trying to prove that it's less than or more than, we're going to use not equal to as our alternative. If it had said less than or more than, we'd use that symbol, but when it doesn't tell us or when it just uses not or is, we have to test both directions. So in this case, the alternative hypothesis would be HA colon mu is not equal to 25. For the next one, HO P equals 0.32. So the 32% of adults is the proportion that we're trying to isolate. Our null hypothesis, HO P equals 0.32. Again, this doesn't say whether we're trying to test that more adults believe that or less adults believe that. For that reason, we need to use a not equal to alternative. So the alternative would be HA P is not equal to 0.32. For the final one, less than 3/4 of the day is spent awake. There we would use HO P equals 0.75 because 3/4 is 0.75 as a decimal. And if we're trying to prove less than, then our alternative would be HA colon P less than 0.75. Again, this exercise is really just getting us used to setting up. Here's what we're starting with. Here's how we're trying to disprove it. And really, hopefully, this short lesson just gets you to understand the framework of how these are set up so that you can better understand the conclusions that you could be shown whenever you're reading a study like this. There's two types of errors we can make when we do these statistical tests. The first type of error we can make is a type 1 error. That occurs if the researcher rejects the null hypothesis in favor of the alternative hypothesis, when in fact the null is true. The probability of committing a type 1 error is denoted by alpha. This is something where we use our statistical test. We say, yes, our statistical test worked. We're able to reject the null hypothesis in favor of the alternative, but in reality, that's not what actually should have happened. For the rejection region, that's this area here, where it's far enough away from the mean that we say that we're going to be able to statistically reject, but maybe it fell into this rejection region just by random chance. Again, the example I used before is if we're trying to say the average height of a college student is more than 68 inches. Here's 68 inches. in our middle, we take a sample that's directly out of the basketball team locker room, where we find that the average height of a college student is 71 inches. It's so far away that it's in the region of rejection. We say, no, it can't possibly be true that it was 68 inches. And it turns out that the average height of a college student is 68 inches. We just happened to get a sample that was so far away from what we expected because of random chance. That's what this graph is showing. It's showing that we make this type of error where by random chance we reject something that shouldn't be rejected 5% of the time if we set our alpha to 0.05. Basically, when we do a statistical test, we have a choice of how to set that alpha and how to say we want to be this percent sure in order to publish our findings and say this is true. A type 2 error occurs if the researcher accepts the null hypothesis when in fact it's false. The probability of committing a type 2 error is denoted by beta. Beta is a much more difficult concept to grasp. Basically, beta is saying that we should have been able to reject it, but we couldn't set up a test that showed it. So maybe we all know that the average age of a college student is less than 50. But it turns out when we took our sample, it wasn't far enough away. We didn't take a big enough sample the way we did it, and we're not able to prove it. So we have to leave it as we don't have evidence that we can prove that the average age of college student is less than 50. And it turns out we should have had evidence to say that. So a type 2 error occurs when we should have been able to prove something, but we were unable to prove it. The American justice system has the following situations. We start out and we're supposed to assume that the person who's being accused is innocent of the crime. If there's significant evidence presented that that's false and the prosecution brings forward everything that shows that no, this person is not innocent, in that case, the jury is supposed to reject the null that the person is innocent and instead accept the alternative, the person is guilty and should be sentenced to whatever crime entails. If we use this framework, what a type 1 error would be is sending an innocent man to prison. We've rejected the null that the person's innocent in favor of the alternative that the person is guilty, when in reality the person did not do the crime they're accused of. A type 2 error is let a guilty man go free. So we have somebody in front of us in court who actually did commit the crime they're being accused of. We don't have enough evidence to show that they've committed that crime, so they do not have to pay the penalty for that crime. These two types of errors, I'm hoping show you that the tolerance that you want to set this for is very subjective. There's times where making a type 1 error is much worse. There's times where making a type 2 error is much worse, but neither is ever good. I would say that there's many people who would tell you that they'd rather have 1,000 guilty people go free than one innocent person in jail. There's other people who might say their tolerance would be 10 to 1. It's not an ethics class, so I can't really tell you where I would put it necessarily, but I can tell you that it's easy to set it too high or too low in either direction. You definitely want it to be the case that innocent people are not in jail, but you also want it to be the case that if people are committing crimes, that they're paying the penalty for those crimes. So this hopefully highlights the idea that as you're creating these statistical tests, there's trade-offs in how confident you want to be. If you demand to be 99% sure that, or even let's say 99.99% sure that this new vaccine is safe for the public, then it's going to be really hard to get it approved, and maybe a lot of people who need the vaccine are not going to get it in time. As opposed to if you tell me that you only need to be 90% sure it's safe, then maybe we rush forward a vaccine that is not safe, and many people, as a result, have negative consequences from the vaccine. The idea is how sure and how confident you want to be isn't as easy as I want to be as confident as possible. You set the standards too high, it's going to be impossible to prove anything. It's going to be impossible to use these methods, basically. So type 1 and type 2 error are both important. We have to understand that there's a trade-off between them. This shows in table form what the possible situations are. Here on the left is the conclusion from my test of hypothesis. Either I rejected the null hypothesis, which makes me say and assert that the alternative is true, or I failed to reject, which means that we have to continue to assume that the null is actually true. If the null was true in real life, this is a correct decision, and this is a type 1 error. If the alternative was actually true, then accepting the null is a type 2 error. We should have been able to reject it, and rejecting the null is a correct decision. So when you state error types as what could have happened in the study, you state it as we believe, this is for a type 1 error, state the alternative hypothesis. In reality, state the null hypothesis. Type 1 error for the justice system, we believe the person is guilty of the crime. In reality, the person is innocent. For type 2 error, we believe the person is innocent of the crime. In reality, the person is guilty of the crime. For the following scenarios, state what type 1 and type 2 error would be. I'm going to do the first one and have you guys try the next two. So in the first one, the null hypothesis is student athlete is not using steroids. The alternative hypothesis is student athlete is using steroids. So if I was going to do type 1 error, we believe a student is using steroids. In reality, they are not using steroids. A type 2 error, we believe a student athlete is not using steroids. In reality, they are using steroids. Again, I'm hoping that you can see that both of these situations are bad. You definitely don't want to accuse somebody of doing something that they aren't doing, but you also don't want to let certain athletes compete on a playing field that's not fair, where they have an advantage over the other athletes. I want you guys to try for the second and third example to figure out what would a type 1 error be in this situation, what would a type 2 error be. Give you some time to work on it. Second example, a type 1 error would be, we believe there is not alien life on this planet. In reality, there is alien life on this planet. So we rejected the null. We believe the alternative. In reality, the null was true. As opposed to a type 2 error. Type 2 error, we believe there is alien life on the planet. In reality, there is not alien life on the planet. For the final one, the null was it will not rain today. The alternative is it will rain today. The weatherman's decision, and wonder whether it's worse or better, which error you could make. But in this framework of a hypothesis test, a type 1 error is, we believe it will rain today, when in reality it will not rain today. A type 2 error would be, we believe it will not rain today, when in reality it will rain. I'd say the most important thing you can take from all this, and again, I know I'm just giving you a very introductory view of a lot of incredibly complicated topics, so if you're confused on a lot of what I'm saying, I understand that. That said, really what would be most useful to you later in life is recognizing what these p-values mean and how to use them. There's a variety of statistical tests that can be run to try and determine how effective a new drug, device, or procedure could be for dental practice. Reading a clinical study, they will list p-values for these studies, which represent their level of rejection. Basically, this p-value can be compared to alpha to determine whether the conclusion should be reject the null or fail to reject the null. A properly conducted hypothesis test will generate a test statistic. This test statistic will essentially tell you what the probability of seeing the sample data by random chance is. We compare this value to our allowable type 1 error probability alpha. P-value is less than alpha, we reject the null and say that we've proven the alternative. If the p-value is greater than alpha, we fail to reject the null and say there's not statistical evidence to prove the alternative. So basically, the lower these p-values are in a study, the higher the statistical probability that what they wanted to prove is correct. Study of a new toothpaste with lower fluoride content found that when compared to the leading brand, it performed better in preventing cavities with a p-value of 0.0279. What is the test decision at alpha equals 0.05 and alpha equals 0.01? In each case, we want to compare the p-value to alpha. When we compare it to 0.05, 0.05 is larger than 0.0279, so we would reject the null at an alpha of 0.05. If our alpha was 0.01, 0.01 is smaller than 0.0279. We would fail to reject the null at an alpha of 0.01. Put this in terms of percentages. When we performed our statistical test, it showed us that we were 97.21% sure that this toothpaste was better than the old one. If we set out before doing the test to say we have to be 95% sure to say it's correct, well, then we met that threshold. 97.21 is beyond 95% sure. For that reason, at an alpha level of 0.05, we would publish our findings and say, yes, this is better at preventing cavities. But if we'd said we need to be 99% sure and set our alpha at 0.01, when we did the statistical study and found out that we were only 97.2% sure, we couldn't publish and say we're 99% sure of this outcome. So if we're reporting a p-value of 0.0279, it means that we can reject the test at 0.05, but we have to fail to reject at 0.01. I want you guys to try number 2 on your own and see whether you would reject or fail to reject at the 2 given alpha levels. So a new type of drill is found to cause less pain than the leading brand with a p-value of 0.1721. What's the test decision at alpha equals 0.05 and alpha equals 0.01? In both cases here, the p-value 0.1721 is greater than the alpha. When the p-value is greater than the alpha, we fail to reject. So we have not found statistical evidence that the new type of drill causes less pain, even though this test shows that we're 82% sure it causes less pain. We need to be 95 or 99% sure based on our alpha choices. So if we're only 83% sure and we need to be 95 or 99, we're not sure enough to publish. We can't say based on this p-value that we definitely think this new drill is better than the old drill.